Thanks for being here today. We are very happy to welcome Olivier Couture, who is going to present, next-gen echography, incredible imaging capabilities and devices.
Well, thank you for the invitation. So I'm not, my lab is not very far from here. It's at Cordelier. It's in the 6th arrondissement. The building is older, and the windows are not well insulated. But so I'm going to talk about super-resolution ultrasound imaging as a technique that I've been developing for more than 15 years now. So obviously it's the work of tons of people. And full disclosure, I also have a startup. So some of the things I will show will also be involving a startup. So what I want to talk about is the basic physical limitation of ultrasound that limits the quality of the imaging at the beginning. And the first thing is to say what is our main interest in our lab is the microcirculation. Microcirculation is small vessels that are below 100 micron. And this is where there's the exchange between oxygen and nutrients with the surrounding cells and how the nourishment happen. And what's interesting about the microcirculation is that it's very well adapted to the purpose of the organ itself. So we can imagine the microcirculation around the alveoli to benefit the exchange between gas and the surrounding and the blood, or the nephron, which has a very interesting microcirculation, allowing different level of osmosis exchange at different levels of the kidney. In the brain, we know that the microcirculation actually respond to the function of the brain, and we also know that the microcirculation is impacted in diseases such as in cancer, for angiogenesis, but also in diabetes. So one of the issues with imaging the microcirculation is that it's a trilemma. Actually, it's the three version of the dilemma. We have to choose between having a very nice resolution, such as here in transpirarization, or going in depth, or having a non-invasive modality. So we have to choose 2 out of 3. When we do medical imaging, usually we use a non-invasive and depth conditions, but when we want to go closer in the detail of the biology, we choose very invasive methods such as transpirarization for having very nice resolution deep inside tissue. So ultrasound has its own dilemma. The dilemma in ultrasound is between penetration and resolution. And this is driven by the wavelength. So basically, if we want to look at the human fetus, we will go at 3 megahertz, which is a wavelength of about 500 micron in the ultrasound wavelength. And so that will allow us to see a fetus down to maybe 15 centimeter in depth, because the penetration will be enough. But if we want to see a mouse fetus with a comparable resolution, relative resolution, we have to go at much higher frequency, much shorter wavelength to get a better resolution. But then we can only penetrate for maybe 1 centimeter. So that's the trade-off in ultrasound. Now, this trade-off comes from the fact that when we image with ultrasound, it's a bit like optics. It's based on ultrasound echoes. So we send, for example, ultrasound pulses that are focused, and what the goal of the ultrasound imaging, the basic one, is to distinguish objects. And as in optics, to distinguish objects, the objects have to be far enough apart that their echo will not interfere with each other. So if we're at a high frequency, 2 objects that are maybe 100 micron apart, we will be able to distinguish them. But if we lower the frequency, we extend the wavelength, we're not able to distinguish them anymore. Then there's the other part of the trade-off, is because basically as the frequency increases, as we shorten the wavelength, the attenuation increases quite drastically. And the worst attenuation that we will come in contact with is, for example, the skull bone, which attenuates sound very rapidly and ultrasound very rapidly. And so this very high power of the frequency makes such that we have to use long wavelength and high frequencies to have a better longer wavelength, short frequency to have a better penetration. So this is the basis of the trade-off. Now, They had something like that in optics, because in optics, they had this trade-off of resolution. So they had to distinguish, for example, points, a bit like us, same resolution problem. And so since they were using wavelengths that are in the order of a few hundred nanometer, their resolution was limited to a few hundred nanometer, or like about half the wavelength. And so for example, in this case, if you observe with fluorescent markers the surface of a cell, you could have a certain resolution to a certain extent due to the limitation of the resolution of the microscopy system itself. In 2006, this was bypassed in optics, where to actually improve the resolution from the typical hundreds of nanometer limit, they've started to acquire it differently. So they took the same cell, but rather than seeing all the fluorescent marker at the same time, they took a movie and made such that the fluorescent marker would blink. So that in each of the image, the fluorescent markers are never interfering with each other. So since they don't interfere with each other, they could pinpoint their center, because the center is not biased by interference anymore. And so they could actually compose an image with a much higher resolution by taking the point of each of these centers in the image and eventually gaining a much higher resolution. So they got maybe a factor of 100, 10 to 100 in resolution gain in optics with super resolution optics, and they got a Nobel Prize for that. So what we did is that we took the same principle. And so in ultrasound, our contrast agents are microbubbles. So they're tiny bubbles that we inject in people. It's been injected for millions of times already. In Europe, it's called Soneview. They're tiny bubbles, a few micron in diameter. They fit into capillaries, and they actually enhance the signal of the ultrasound. They enhance the signal of the ultrasound because it's a strong echo. It's a pocket of gas inside liquid, and so it scatters sounds quite a bit. So on the left, you have, for example, an imaging of a kidney, a transplanted kidney, as it is perfused. Second, as it is perfused by the contrast agents. And so they use this to assess the perfusion of tissue. The speed at which the bubbles come in determines the perfusion of the tissue. So this is used, for example, for transplanted kidney at Necker. So this is an image that we've taken at Necker. And so what's interesting about these bubbles, it's very particular for a contrast imaging modality, is that we're sensitive to the picomolar concentration. A single bubble, so these points are single bubbles, can be seen down to 10 centimeter in depth. And that's a 1 micron bubble. So you can see an object that's 1 micron, 10 centimeter in depth in tissue. So that's a very high sensitivity. And this sensitivity comes from a very interesting thing in nature, is that it's a coincidence that a bubble the size of a capillary will act like a gas, it's a gas surrounded by liquid. So you can see it as a mass spring system, and it has a resonance frequency. And the resonance frequency of a bubble that's 1 micron in radius will be in the scale of hundreds of nanometer, well, in the resonant wavelength. So it's a great thing of life that this bubble would be resonant exactly at that point. So if you think of a bubble the size of this point here, it will in fact have a resonant wavelength much larger than itself. And it will be able to couple two scales in the body, in this case. And that's what we're going to use. So basically, the principle that I'm going to show is that in optical microscopy, they had tiny fluorescent molecules that maybe was a 1 nanometer in diameter, or even less. And they could couple it, they could actually emit a wave that's hundreds of nanometer in scale. And in ultrasound, it's going to be the same thing. We have a tiny object, that's a micron, that actually have a wavelength that can reach much deeper region because it's a wavelength that's much bigger in itself. So we're not going to see cell structures.
Just to make sure that I understand. So it's make the region that we can reach more profound, or it's make a bigger signal that we see on the picture.
So basically, when the bubble will vibrate, it will emit wavelengths that are hundreds of times bigger than the object.
Okay.
So since a long wavelength, it penetrates far.
Okay.
So if we were at the same, let's say, if we had wavelength of 1 micron, the size of the bubble, well, it would never penetrate very far. But basically, we couple the scale of the wavelength that can actually penetrate far with a tiny object that oscillates so much that it will generate these kind of wavelengths.
But how do you excite the bubbles if you can't reach it?
That's actually the ultrasound that does this. So you send a sound, the
Yeah.
bubble starts vibrating, and
Okay.
becomes a secondary source.
Yeah, but you told us that the ultrasound do not penetrate depth enough.
Yeah, but that's because we use low wavelength.
Okay.
So these low wavelengths normally should couple large objects.
Okay.
Well, so long wavelength will couple
So
large objects.
long wavelengths
Yes.
go further
Yeah.
and excite the bubble.
Yeah, exactly. And the bubble is very tiny with respect to that long wavelength, but it still couples with it.
Okay.
So it's the same thing as using a very large wavelength with respect to the fluorescent marker, because the fluorescent marker actually activates at these wavelengths. So it's yeah.
And to be clear, the catch is that usually if you go deeper, you have a low spatial resolution.
Right.
But here, because you're going to acquire a movie, you're going to be able to do super resolution and so to pinpoint the location of the bubble.
Exactly. So basically what we do in cell structures where we would pinpoint an object on a cell structure and with pointillism try to reconstruct it, what we're going to do in ultrasound is very simple. We're going to image bubbles that are flowing in vessels because they're only in vessels. That's also the very important thing about microbubbles. And we will pinpoint their position, their center position, and we will create an image out of that. So that's the basis of ultrasound localization microscopy, which is the equivalent of single molecule localization microscopy in microscopy. So when we demonstrated it in animals for the first time, what we did is that we coupled an ultrafast scanner. And so these are new types of ultrasound scanners that can go at much higher frame rates. We could go at up to 20,000 frames per second with it. It's also programmable. So this is something that we were discussing. It's fairly new in ultrasound that we can program. Before that, it was purely electronic. So this is something that made ultrasound not evolve as fast as MRI, because MRI you could always program it. While in ultrasound, you had to change the electronic. And this is because we produce a lot more data. And because before recent events in computer science, we could not actually process that data fast enough. So we had to use electronic to actually create an image. So we coupled it with contrast agents, and we did imaging of a kernel plane of a rat brain without a skull. And so when you do that, the first image that you see is the brain that you see. This is a cut like this, a kernel, and there's no skull on top. So that's much nicer. And then when we start the imaging and we inject the bubbles, the contrast agent, what you're going to see is that then here we implement a filter to just see the bubbles that are moving around. Then we pinpoint their center position. And then since the bubbles are flowing inside each of the vessels, we just track them in each of these. And then since we're going at very high frame rate, we can go up to, we can do maybe 100,000 images within 3 minutes. So that makes us about 1 million tracks. And from that 1 million tracks, we can reconstruct an image like this. Yes.
Is the number of bubbles in the movie accurate, or is just for illustrative purpose? Is there as few bubbles?
Well, actually, no. This is actually they're usually we try to get about 100 bubbles per image. And so
In the whole volume.
In this case, in the whole plane, we have maybe 100 in general. Like this one was maybe a bit diluted for the purpose, but we have about 100 per plane. And then they're track in time. So the same bubble is actually in several images. And then we take about 100,000 images to actually reconstruct this image here.
And how do you deal with the fact that they go out of the planes?
Well, we don't, and that's the beauty of the brain and the kidney, is that they stay. There's a planar structure of the brain. So actually, that's why we demonstrated it in the brain, because the cortex is radial. But actually, if you start looking at these vessels here in the striatum, you see these vessels, they're out of plane. And here, the velocities of the bubbles have nothing to do with there's nothing real there.
And Why do you acquire a plane?
Why do we
with,
acquire a
ultrasound,
plane?
like,
So,
what is the physical evidence?
so basically, when we do an image like this, we have to sample each of the channel maybe at 30 megahertz. So we have to have like 30 million samples per second per channel. This will have 128 channels, so it accumulates a certain amount of data. And so the way imaging is done in general is that you have a single line of transducers, and that single line of transducers will only be able to reconstruct everything that's inside the same plane of that line. If you're out of plane, you cannot reconstruct the position because you're not informed about the position because you don't have this extra position. If you want to do 3D, you need to have a matrix array. And then the matrix array, like the common one that we use, is 1024 channel. And so rapidly n square problem of the channels that you have to sample like at 30 megahertz.
Okay, and in practice, each channel for you, it's like a small microphone?
Yes, so you have a tiny little transducer. So transducer is something that converts sound into electricity, or the reverse, electricity into sound. So that's why when we send a pulse, in fact, we send an electric pulse. The electric pulse is converted into sound by the tiny little transducer. It propagates, then it's reflected from the structure inside. It comes back to the transducer. The mechanical wave gets converted by the transducer into electrical wave, and then it gets read. So there's a transmit electric channel and there's a receive electric channel. And so we have to sample the receive channel with a very high frame rate. And so we produce quite a bit of data in 2D already. So when we switch to 3D, it becomes a lot more complicated. And I'm going to get into this, but the 2D is kind of to show the principle. And so, just so you know, the way we do the ultrasound, that's maybe to give you a bit of understanding of the complexity of it, is that we send, in our case, a plane wave. So we send, like, for each of the transducer, we send the same wave at the same time. It can be skewed, it can be compounded. And then we collect the echo from each of the little source, which sends a spherical echo. So then we collect it on that series of little transducer. It makes these hyperboles. And then the principle of beamforming is to convert these hyperboles with a process that we call delay and sum. So we deskew these hyperboles and then we sum them to determine the intensity in each point. So actually the reconstruction of the image can be actually quite a long process in 3D, because we have maybe 32 by 32, 30 megahertz. So we get a lot of samples just to get just the image, not even the ULM.
What is the size of the image typically?
Well, in this case, that's probably about 2 centimeter by 1.5 centimeters.
Yes, but the number of voxels.
Well, usually we reconstruct with a resolution of half the wavelength.
Okay.
So let's say here in this case we're at 15 megahertz. The wavelength is 100 micron. So half the wavelength is 50 micron.
Okay, 50 microns on 2 centimeter. 50 microns.
Yeah. Well, it's a few hundred.
Okay.
It's a few hundred pixel by few hundred pixels. And then when you do 3D, you do another like few hundred pixels, and then you do 100,000 of that. So basically, when we do 3D for a single mouse for a few minutes, it gives us between 300 to 400 gigabytes of data for a single mouse.
Okay.
And so without GPUs, it was impossible a few years ago.
And also because for like MEG, EEG, they have a lot of noise, but here you don't have, I mean, the images look fairly clean, so there is no noise that comes from the body.
Well, actually, the body doesn't create a lot of ultrasound by itself. The noise is mostly electronic. It's the electronic noise from the machine, because basically what's interesting is that the dynamic range of ultrasound is a bit like our ear. Like our ear is a logarithmic scale, right? Like we have a huge difference between like 120 decibels and 30 decibels. In ultrasound, it's the same thing. So we're in a logarithmic range. So we can have like an 80 decibel range between the signal we have at the top and the one at the bottom. So it's a question of like sampling, and then it creates electronic noise. That electronic noise, well, is summed through that beamforming process, and it creates like a gray background. So that's our problem in ultrasound. So after we've acquired and beamform, we get these ultrasound image, that's the standard image. Then we do filtering. So to extract the bubbles that were injected in the body. And so we use very often their motion to actually distinguish them from the background tissue. And then we do localization, we pinpoint their position, and then we do tracking, and then we accumulate all the tracks. And that's what we do for superresolution. So initially, when we showed how it worked, we started with these kind of images with standard ultrasound Doppler. And then in the same region, we could obtain something like that. So it was about a tenfold increase in resolution. And another interesting thing for ultrasound is that since the bubbles are moving, we can determine their velocity at every point. And so we can and it's isotropic. So basically we can know their direction, which is different than in standard ultrasound Doppler, because Doppler is directional. In this kind of technique, we can actually determine the velocity of each of the bubbles, and you can actually see that the larger vessels have a higher velocity at their center. So basically, you can bring back Poiseuille flow and everything.
And just like on the previous image, it's not clear to me where do the bubbles come from, because like you have a column, I would expect them to flow from the big artery into the.
Well, in the case of the brain, usually the arteries come from the top and then plunge in the brain, and then they come back through the network of capillaries, and then they go up through veins here. So everything that goes down is in the in the artery, in the cortex. Everything that goes up is in a vein. But it's not the case here.
Okay.
This side.
Okay.
And so one thing that's important to know is that ULM is actually, the resolution of ULM depends on your sampling. So it's quite a different way of doing imaging. So first of all, we use tracks. So it's not pixel-based, it's not voxel-based. When we convert into images, we take the tracks and we sum how many tracks pass into a specific voxel. But at first, we just have a series of tracks. And the other thing is that it's a sampling issue. The more bubbles we have, the more bubbles have explored the vessel, the smaller vessels. So the more we wait, the better the resolution we can get. So if we were to image for an hour, we could get to the capillary bed. If we image for a few minutes, we only get to the arterioles and venules.
Because the bubbles are small enough to get into the capillaries?
They get everywhere. They're about 1 micron, so they get everywhere. It's just that when we inject bubbles in somebody, we maybe put 1 bubble per 100,000 red blood cell. So when you look at intravital microscopy and you look at the capillary, you see that the red blood cells are passing one by one. So you have to wait for a bubble to pass through the capillaries so that capillary is observable. So there's a problem of just waiting for the bubbles to pass by.
And practically, your mouse is like sleeping. The mouse is like sleeping, or just.
Oh, it's in this case it's anesthetized. Yes.
Okay.
Yes. Yeah.
So you have to wait for like minutes.
In this case, the mouse was anesthetized for a few minutes. In this case.
And you can't just put a crazy amount of bubbles.
The thing is that that's an interesting question. Is that if you put a crazy amount of bubbles, the bubbles then become non-isolatable, so they interfere with each other. So you break super resolution.
Okay. So it's not a question of death. It's just.
Well, actually, you can inject a lot of bubbles in people and in mice. It's not very dangerous because they get dissipated through the lungs within a few minutes.
They are going to inflate.
No, but basically, there's a point where we're like, I will show you image on the sheep, and the sheep, there's an issue with the sheep, like they were using a lot more bubbles than we expected, so we started like injecting a lot of bubbles, and at one point we said like it will float up at one point, right? and they were fine with it, but basically it's mostly because of the physics of it. Like super resolution is based on isolatable objects in each of the image. When they're too dense, you cannot do super resolution anymore. And so there's been a lot of development. So at first we showed it like that's more than 15 years ago with some of the colleagues that you have at Paris Biotech Santé now. But since then it kind of picked up. So the ULM has been used in pretty much all organs in the brain, in the kidney, in the heart, in the lymph nodes, in cancer, in muscular, skeletal. So there's tons of lab working on this. There's people that do it on different diseases now that I'm going to show a bit. But it's quite a lot of people are working on this. A few examples that I found in the literature is, for example, people that have used ULM to characterize aging and Alzheimer's disease. And a lot of diseases are linked to microcirculation impact. In this case, what they could show is that the Alzheimer alpha beta plaque was correlated with the lack of microcirculation. So they could actually correlate Alzheimer's with the detection of these vessels. There's people that did tumor growth, but the issue with tumor is that the out-of-plane problem becomes really problematic because since the vessels are chaotic, they mostly go out of plane. So I haven't worked on tumor until we add a really good 3D imaging system because I felt like 2D was not enough for tumor. And an interesting one that contradicts what I just said was the fact that, for example, in this case, that's a pancreatic tumor in a human, where they show that, for example, and you look at the scale bars, 10 millimeter, you see all the vessels here. They're the small vessels that are now feeding the tumor that have been generated by angiogenesis, and that was actually performed in a live patient. And so some other colleagues have also showed that you can do some transcranial imaging in 2D with it. And I'll show you that after that, the goal is to go in 3D. And obviously, there's some machine learning on this. Most of the machine learning currently is done on the initial image construction mechanism. So basically how you extract the bubbles, how you localize them, how you track them. And so that's the main purpose, because there's not enough data to redo training for the end result right now.
So just on the acquisition process, because you mentioned doing it on live patient, how do you make it so that you're really in a single point and you don't move at all? Because I guess because of the high frame rate, a single movement is going to cause mayhem.
Well, actually, in this case, they probably do the same thing as what we do in the kidney for patients, is that you use short apnea. You ask the patient to stop breathing for 10 seconds, and then you do your imaging during 10 seconds, and that's what we have.
Is it like handheld and it's steady enough?
It's
or do you do registration and post-processing?
Well, the problem when you're in 2D is that you can only register whatever is in the plane. So it's always going to be limited. And the radiologists, when they can see the image on they have a very high resolution, in fact. When they see the image online in real time, they can actually they move their hands slightly to always be on the same plane. But they're actually pretty good about that. At one point, when we got to the brain, we thought it would be nicer to have a helmet. And in the end, we asked the neuroradiologist to just show us how they would hold the probe for a few minutes, and they were really good at it. So actually, we're better than a helmet, because then the helmet you have to adapt it to every head and etc. While the neuroradiologist was used to just put the probe on the head. And so after this evolution, what we tried to do, and this is something that in our field is untypical, open science. In your field, that's the normal. We tried to expand the use of ULM, and the strategy that I had was to try to make it usable by the most people as possible. To try to transfer it to clinical machines, because what I've shown you in the animal was with ultra-fast systems that are not available in the clinic. So in the clinic, you have maybe 50 frames per second. And in the programmable scanner, you have like 500, 1,000, 5,000 images per second. So it's a big difference in how you can track bubbles and things like that. and eventually try to create a system in 3D that can actually do ULM in 3D. So that were the three strategies. So the open science, this is actually not very common in our field, right? It's the fact that we publish a paper with the data and all the code. This is something that we inspire ourselves from the computer science world. And so, for example, this paper, we put like 2D data for several organs and all the code to achieve it. And the experiment actually it was very uncommon. We ended up I think there was 140 terabytes of data that was downloaded from that for that data set. So in the end, it's a good experiment. So it was a good transfer from computer science. And so if you ever want to work on this, so there's the series of code that we call PALA, which has everything, that has data, that has metrics, that has a code to run in 2D, and the 3D will come out in the next few weeks, in fact. So the first stage was trying to use ULM in clinical brain. And so using clinical tools, that's the first stage, because that's what we have access right now. So it's to address a few issues. So it's issues very often when people don't have access to MRI. It's either because you're in intensive care. So I was saying that, for example, just moving certain patients can have like an 8% mortality rate for some patients in intensive care because they're so fragile. So they don't bring them to MRI, they don't bring them to the CT. We can think of neonatal neuroimaging. This is also something that's very difficult to perform. Like the people that work on babies with us, they say that, well, obviously they will not put them in an MRI until a few days, and they will maybe do it once. In the ambulance, for example, like now they're trying to put CTs in an ambulance. There's one running around in Paris these days. It's actually quite a heavy system. It takes 4 people. It costs €1 million. But this is actually for early diagnosis of stroke. And also high throughput, because you cannot put everyone into the MRI.
Basically, they inject the marker on scan on the site.
Right now we're not in the ambulance yet on the ultrasound side, but these 3 were done. Yes. The ambulance would take a bit more time, and the ambulance only happens when you're really well established in the hospital. But the ambulance, for example, like there's a real CT that is based at the PTA and does round in Paris. So when somebody calls with suspicion of a stroke, they can send this unit, and they do the CT in the ambulance so that they can treat the person right away. So our hope is that we can also do that with ultrasound. And so the example for this is that this is what justified my ERC grant, is the fact that right now you need MRI and CT to distinguish 2 types of stroke: the ischemic stroke, which is linked to a blockage, and the hemorrhage stroke, which is linked to a rupture. And you have to treat these people within 3 hours. So within 3 hours, they have to get to an MRI, get the scan, get the radiology check, and then get the treatment. And so our hope was to use ultrasound, which has its drawback, like the fact that it has in normal situation a terrible resolution, but it's still portable. It has low cost. It's just that the problem is that without super resolution, the image quality is very terrible. So an example of what we can do in human now, this was done at Bichat Hospital. It's a probe that's placed on the temporal window. So there's a place here at the temporal side that the skull is about 4 millimeter in thickness. So it's less thick than the rest of the skull. And then what we wanted to see in the case of these patients, which are called moya, are vessels that are coming from, this is the middle cerebral artery here. These vessels here. And actually, that's the ULM. So in Doppler, this is what you will get. And this is MR angiography. So 3D MR angiography, so you don't see them. And we wanted to see them because these are the vessels that are sprouting from the main vessels to actually feed the brain that was not appropriately fed before. So one of our first study in the clinic was to just use standard clinical care, so that's maybe 40 frames per second, and then just look at how the bubbles were going in all these vessels and trying to make an image that could be of a benefit for the doctor. So if I don't have a skull, I don't have a skull right now, but this is the circle of Willis. This is the basis of the vessels that you have at the basis of your skull that feeds the rest of the brain. This is one of the main artery. This is the middle cerebral artery that goes from that basis of the brain and goes to your temporal side, and this is one of the main one. And actually, it shows all these tiny vessels that actually are feeding the rest of the brain and that are impacted by this disease called moyamoya. And so, as you can see, well, we know that in 7 Tesla MR angiography, we could see these vessels, but with 3 Tesla, it's not sensitive enough. So it's possible with ULM. Another stage was to use it on babies. So we did that with the team in Germany. They were already injecting bubbles in these babies to actually see the perfusion. So we said, like, can we implement our methodology on your data? And so these are babies that actually had stroke, because there's a lot of newborn with strokes. That's one of the risk factor for newborns. And this is the cortex of the baby, and this is the top. The other layer on top of the brain is the meningia. And what we observe is, I don't think anybody was able to observe that before, is that the brain of the baby is so plastic that when there's an ischemia, when there's lack of blood, it will create these new sprouting vessels to try to feed itself. And this is not something that can be seen otherwise, because this is actually quite precise. I think the scale bar there on the left is 1 centimeter, I think.
And to be clear, because the skull of newborn still has a gap, it's much easier for you?
Yes, we go through the fontanelle, which is so basically because the newborn has to come out, the skull is not calcified completely, so that the skull can move a bit. It only calcifies later, so we use this window to actually make a better image. Because the skull is really terrible. I'll show you how bad the skull is afterward. And so when we look at the entire brain, we can have very interesting images of the entire vasculature of the newborn, giving access to vessels that usually we don't see, or if we had a method to see it, it would be impossible to bring the baby to that site.
And you were talking about strokes, but how long is it to compute, like from the start of the acquisition to you get like a proper image with velocity?
Well, right now in 2D, it's pretty much real time. So basically, if you're at 40 hertz, you have 100 bubbles per image, you track them, all this stuff. Our code runs on a modern computer about real time. Like the same period it took to acquire a few minutes, will give you a few minutes of it. In 3D, we got a beamforming is about 1 hour for like a few minutes acquisition, and then the ULM is another hour because we're in 3D. So that's the.
There's still a scaling issue.
Yeah, there's a scaling issue.
Okay, so you mean that in 3D you acquire and then you wait for an hour and you see what you have
Right
acquired?
now,
Okay.
yes. That's obviously that does not fit with the ambulance issue, but we know from experience that when we work on a problem and everybody says like, yeah, the calculation time is too long, it naturally resolves itself within a few years, so we don't necessarily care that much.
So for these images, it's just a 2D slice, right? So it's just like for the baby like this. So if my stroke is anywhere else, I'm out of luck.
Exactly. So that's the main issue with 3D is that you have.
I mean, especially for 3D might not be possible, right? Because I can only scan where there's no skull, right?
Yeah.
So I can only scan basically in layers defined by the sutures that I have.
So basically, it also drives what we call the user dependence.
Mm-hmm.
So when you go to get an MRI or a CT, it's a technician, press the button. The radiologist has said, I want a T1, a T2 MRI, stuff. They press the button and it runs a scan. In ultrasound, the problem is that when you have a 2D, the quality of the image depends on how well the radiologists have placed the probe. Mm. And so that means that radiologists probably knew where to see already, and then press a button to acquire for a certain amount of time. It's already how it's used currently. Ultrasound is used. It's very user dependent. If you get a great radiologist, you get a great result. But if most radiologists they don't want necessarily to touch it because they're not trained appropriately, and so that's the main problem, is that they knew where to look for.
But do they have like live feedback when using this type of machine, like a regular ultrasound?
But not ULM. So basically, they look.
They take a first regular ultrasound,
exactly.
then switch to ULM.
So you have like what we call B mode and Doppler. So you get like a normal like grayscale and then the Doppler, and then they look around and okay, that's probably the bad part, and they press the button, we inject the bubbles, and that's what we do. And obviously we want to get out of that. That's my main line of work.
And to be clear, who gets training to handle ultrasound? Because like, Cécile, she's a radiologist, but it's not clear for me if every radiologist gets some training with ultrasound or not really. Like
Normally
it's a specialty.
But the problem is a lot of them will say, that's not my main tool, and they will send them to the most expert, right?
In France, every radiologist has to do ultrasound, but this technique is too specialized. So in my experience, it's not a daily, it's not a routine.
ULM is not, for sure. But even like I work with Necker adult imaging, for instance, and it's obvious that the radiologist there has been like an ultrasound fan for like 30 years, has published tons of paper on the subject. He's really used to it, and to him, it's the go-to method. But there's a cultural clash, between different radiologists. Some of them they don't trust, or they don't even trust their own skills for the ultrasound, and they say, "Yeah, let's do an MRI." That's I don't know if what's your feeling.
It's very operator dependent.
Exactly.
Okay, and because you have this notion that the probe is moving, in practice you neglect this movement because you acquire things so fast.
Yeah. Well, that's what the point. The problem is that then when you do ULM is a long process with respect to all the other imaging. Usually, an ultrasound is something quick that goes fast, and you scan, take a plane, press a button. So in obstetrics, it's pretty obvious. Like they move around. I see the spine. I press the button. I measure the spine, and I move to the heart, and I look at the Doppler of the heart, and so they tend to work very fast, and they know where to look. It's a very different way of working with an apparatus than the other imaging modality. And the issue is that for example, transcranial imaging, it's very difficult to get far in there because some of them do that for many years. So you have like special centers that are very used to it. Many of them will not touch it. I even, in one of the conference on brain surgery, I was even told before my presentation, somebody said, ultrasound is from the 20th century, it should have stayed there. And so that tough crowd, right? So that was kind of the spirit of many radiologists saying like, yeah, it's a dead method. But it has its potential is mostly through its portability and the speed of access, in my view. And you can put that in surgery room.
No,
you can
tracking the small arteries is like something the method is able to do. So I saw people with light sheet and they had cue the mouth and say, okay, so I have plenty of mouths with the same DNA. So okay, hopefully the brain is the same. And for here it's like nice.
Oh yeah, well actually that's that's one of the benefits of ULM is that it actually gives you access to information that you didn't have before.
Yeah.
So that's the main difference. But it's still blocked by the cultural aspects of the use of ultrasound.
Yeah, I know. I see. It's like it sounds old-fashioned.
Yeah, exactly. Some of the image that we've done was not in the brain, was for example in the kidney at Necker Hospital. And the kidney is very interesting on the point of view of microcirculation because it's designed to filter blood. And the way it filters blood is how it's structured. So you have a structure, the glomeruli, which it's a ball of capillaries that will extract the components of blood, and then through an osmotic exchange, it will exchange back inside the blood. So a very good filter. It's basically, it extracts everything and it takes everything that it wants. So probably much better filter than anything else. And so the microscopy structure is very interesting. And so in standard, ultrasound in this case is a standard method. So you have like the baseline, that's the ultrasound grayscale. Then you have the Doppler, and each of the sides you can actually have the Doppler spectrum. So that's why you hear. That's because you have like Doppler shift of the ultrasound. That's the other great coincidence of nature in ultrasound, is the Doppler shift caused by blood from a few megahertz, the kind of frequency that we use, is actually in the audible. So that's a great coincidence of nature that was unexpected. That's why you hear that whoosh, whoosh, whoosh. That's because it's a Doppler shift. And so when we do standard kidney imaging, you put the bolus. That's for perfusion imaging. The rate at which the bolus arrives determine how well it's perfused. But then what we said, just keep acquiring. So we didn't change anything to the acquisition of the patients. We just said, like, keep acquiring while the bubbles are leaving the body. So they're leaving after a few minutes, and they become more rare. And so they're distinct. They're isolated. We can do ULM. So we could do with ULM, with a clinical scanner, we could go from these kind of images, so that's the standard practice Doppler currently, to these kind of images, which gives you a much better sense of the vascular system with the direction that's isotropic in the kidney. So it also has a much smaller vessel. You can see much smaller vessels than standard. But just keep in mind one thing, and that's the example I would give you. This is what you have at 40 hertz, 30 frames per second with the ULM pipeline. And this is what we have with the ultrafast in the kidney of a rat. That's the difference of frame rates give you. And so this is acceptable. This is available in the clinic, and this is not available in the clinic as of now. Well, it's starting now. So, but what's interesting was that we started looking into a bit deeper in what's going on to the bubble. Because as I told you, it's not a pixel-based method. It's I guess you would call it a graph-based method, like in your field. Like we have tracks. Is it a graph-based method?
Particle method.
Yeah, particle.
Lagrange.
So you can look at individual bubbles moving around. So we'll take single bubble. If you look at a bubble that goes up, for example, here, goes up, it swirls around, and it goes down. So this is in the cortex of the kidney that we've seen that, and it's pretty specific. And so we didn't know what it was. Do you have a guess?
It's like the sacs or something.
Pouch?
They have pouches.
So that was in humans. So we went back to the rats because we wanted to have a definitive gold standard. So we did the same imaging in the rat. We did the same kind of separation that I'm going to tell you about. And then we realized that we could have like these swirling bubbles. We're creating kind of sacs in the cortex of the kidney. And then what we concluded was that these sacs were the glomeruli. The glomeruli, they're about 200 micron in size in human, so much smaller than your typical imaging resolution. But it's because of the super resolution that you can actually see this effect. So we tried, then we converted a bunch of, we confirmed it in the rat that it was the right size, the right number, the right position with micro CT, obviously very invasive. And then we went back in the clinic, and what we could do after using this principle is that we could then distinguish the balls that are doing this phenomena and the one that are not. And you can now create an image with where you see all these little balls there, pink balls, there's the glomeruli that we can detect. Obviously, there's a lot more than that, but it's a sampling mission. And in green, you have like the straight bubbles that are moving in the right direction. And all these little pink ones are the glomeruli. So now we have, we've been testing it at Necker. where we use this to distinguish tumors from pseudotumor. So a tumor is a non-functional organ. So it has no glomeruli, or very, very little. So if you do that in a tumor, you see that there's very little glomeruli, the blue dots there. If you look at pseudotumor, so it's a normal tissue, but it looks like a tumor, well, you have tons of glomeruli. So it's a functional organ. So you can now see something that I think is very important, is that when we think of an organ, we think it's a massive cell. It's never a massive cell. It's a structure of functional units. In the kidney, it's the nephrons. So you have like thousands of nephrons that are organized. And so this is where the function of the organ happens. It's not just a ball of cells. You would have that, for example, in the pancreas. You would have the islets of Langerhans, which are producing the insulin. In the liver, you have these hepatic lobules. In the brain, you will have like these conical structure. All these organs are separated in functional units that have multiple different types of cells, and that the microcirculation actually is very important for the function. So now we'll go from 2D, because we try to do 2D because we have access to that in the clinic, to 3D. So this is not ULM. The problem with 2D ULM is that organs are in 3D, obviously. We only got a single plane per injection. So usually you don't want to inject people, even though it's mild, you don't want to inject too many. You have projection artifacts, because vessels out of plane, you will never have the right velocity. You cannot quantify, you cannot do motion correction, and you have enormous user dependency, because you have to select the plane first and then do your ULM. So you cannot do like an MRI and CT, take the full thing and then look at planes by planes. So we wanted to kind of move away from this type of working on the right, like real time, and try to get into an a posteriori diagnosis, so have a 3D. Now, 3D is very complicated in ultrasound, because you have to divide, rather than a single line of transducer, you have now to have a matrix of transducer, so it becomes an n squared problem. So now we have these probes that are 32 by 32 elements, so 1024 elements. They have to be addressed by complex system. And in the case of the first few rats that we were doing, we were producing terabytes per experiment. And so when we do that, we can redo the same experiments. We remove the skull, do the 3D imaging. And in this case, my student has put the imaging on several sites so that we can have the full brain of the rat, which was a bit longer than the probe. And so this is what we can get now with the same process with a matrix probe. Here we have vessels that are down to maybe 20 to 30 microns in size. And we have them from this is the nose area, this is the occipital area. And that's because he made a huge window across the skull. So now it becomes kind of comparable to what you would get. You can fit it with standard anatomy, and then you can do analysis on this, because this is not a pixel base. This is based on like a series of tracks, right? In this case, we have millions of tracks that produce this. And so at first, what you can do is try to look how now it's not just plain. You can actually find the networks of vessels starting from different spots. So that was actually very difficult for us. I think that would be much easier for you. To try to get the network, because basically you have a series of tracks that are sometimes parallel, sometimes they superimpose, and so then you want to know what's the bifurcation of your whole structure. It fits pretty well with the standard anatomy. So this is the standard anatomy of the rat brain, done with slices, and so it fits very well with the standard anatomy. But what's interesting is that since you have each of the bubbles motion and direction, you can determine that, for example, for a bifurcation, you can look at the flow profile. So you can see, like, in the middle, the bubbles were going faster. And here, the vessel is about 100 micron in size. And so within, you can see that it's kind of a Poisson flow. Then it goes at maybe, in this case, 6 meters per second. It gets split in different vessels. the vessels now it becomes slower. And also each of the bubbles have their own history. So for example, if you project their velocity, you can see that the bubbles will go at a different speed, and sometimes their velocity will increase rapidly. But that's just because the beating heart. So when you find your bubble at a specific button, sometimes it will accelerate just because the heart is pumping. And then we try to simplify the system. So now the system looks like this. It's a bit less capable than our previous system, but now we can put it, as I said in the review article, we can put it in the trunk of a small and stylish European car. So we can take this machine and we brought it to a bunch of different animal facility to do research. And so you can do the same thing. And so now what we have, we can do it across the skull. So this is across the skull. It's a small region because we only looked in one region. And so these are the kind of images that we have in 3D across the skull in an animal that is anesthetized for a few minutes and then can be removed from the side, put back in the cage, and we can come back like an hour or a day later to have the same kind of images. And so since it's 3D, you can now quantify appropriately in all directions. So you can basically see the velocity of the bubbles in each of the direction. And well, you have a nicer image. So one of the applications that we've done is, for example, testing the stroke hypothesis that can distinguish different types of stroke. So this is when we block one of the main vessels, the middle cerebral artery, in the rat brain. And you see that here, the vessels disappear. These are the vessels that were irrigated by the middle cerebral artery. So you can use that to see what's going on after the occlusion of the main vessel. And if you take plane by plane, because well, it's a 3D, you can do it plane by plane. So this is coronal, this is sagittal. You see that this zone after 30 minutes loses its blood flow, and then the blood flow comes back because naturally it recanalizes. And you can see it also in sagittal and corresponds very well to what you would see under the MRI for if you look in cleanosity 2. And so you can do analysis. You can see how far the perfusion goes. You can do that for hemorrhage also. The hemorrhage is deeper in this case. And you see it's going to be a different situation. It's only 24 hours later, it becomes a diffuse region. So it's probably an indirect effect of the blood leaking into the tissue. So the problem then becomes, how do you get that in human? So the human has a few issues with respect to rats. First, we have the skull bone that blocks most of the ultrasound, and it has a huge attenuation. And also the mice, we could see the entire brain under our probe. When you look at the human brain, you only have a tiny window to look at a large volume. So you have to diverge, and since you're in 3D, you have to diverge your ultrasound in all directions. So you lose a lot of the signal, what we call the signal to noise ratio. So,
because to be clear, usually it's the inverse, like you concentrate ultrasound on the pancreas or
something like that. You want to, I mean, it's the same thing as an antenna. It's an antenna gain, right? It's the more you have a larger aperture with respect to your focus, the better is you're going to be your image. In the case of the brain images, we have, in the worst condition, we have a small aperture looking at the deep focus. So, and that's a problem that we will not solve, well, not right away at least, is that even if you look at a part of the brain, I'm going to come to that later, you're never going to have the brain entirely. And the thing is that it covers most of the case for strokes, so that's good. Most doctors, the feedback, they say that's pretty good already, but they realize that in this case it's going to be limited to, we're not going to have the whole frontal and occipital zone in the brain, but in many cases it's good enough. So then we move to the sheep, because the sheep parietal bones resemble a lot that of human. So we took all the system, brought it to the sheep area, anesthetized the sheep. We create new sequences, but I'm going to go over that. And then we could get the images are way too far from the rat as I would be pleased, but we see the main vessel. I'm going to try to get it. So these are the kind of images that when we correct for that, we have a 3D imaging, but they're not as well resolved as what we had in the rat because of these questions of the skull and the divergence of
the same guys with the many bubbles we talked.
Yes, yeah. Well, actually, these. There's another thing is that the sheep have this weird system in their brain so that they can cool off their brain with the air they breathe through the nose, and it creates kind of a second lung in the brain. It's kind of called the rhythm mirabile. I didn't know the anatomy of sheep before starting that, and then we realized it was not working that well in sheep. And then the question moving to human. So we've done that recently. It's not completed yet. We still are processing the data. We're now at 90 patients. This is done at Bichat Hospital with the same system that we've done in sheep. Now what we have is these kind of images. So we still have to work quite a bit on this. We have the middle cerebral artery. We have some of the bifurcation in 3D of the human brain. We have some of the perforating arteries that were the one that could be seen on our previous 2D image that we could not see with MR angiography, but we're still processing these images because the paper is not out yet and could be a little while. I'm just finishing with 3D again. So we can also do 3D in the rat kidney. So I've shown you 2D images. We can now do also 3D images, where same process. We detect the bubbles, we pinpoint their localization, and then we track them. And then you can also do the same thing as I told you, looking for glomeruli in 3D. So you can do the exact same thing. You can do kind of maps of bubbles. So that, I don't know, what be of interest for you is that you can basically look at the behavior of each of the bubbles and classify them based on, do they go straight, do they go swirling, do they go fast, do they don't go fast, etc. And then you can encode each of these tracks in your image based on each of their behavior. And so you create a voxel based on their behavior. And so now we can do images like this, where you see certain part of the bubbles that go slowly and straight in medulla of the kidney. We see the glomeruli where the bubbles are swirling, and then we see the rest of the vessels where the bubbles are normally bifurcating. So now we can basically encode the space based on the individual behavior of the bubbles in 3D. And so I'm going to finish on this. I have two, 3 slides afterward. So what's the future of ULM in my view? Well, you can see these bubbles as individual sensors that are moving in each of the vessels. So you can actually gain a lot of information for this, not just like the position or the velocities, but potentially how they interact with the endothelium of each of the vessels. One of the problems that we have is that we create these nice images, but there's no biomarkers for most of the disease now. So there's people working on trying to define new biomarkers that are based on the microstructure of the vessels, but it's still ongoing. And it could be used for the assessment of a ton of disease that have a microcirculation involvement, like arteriosclerosis, stroke, tumors, diabetes, and Alzheimer. We seek to try to avoid user dependency. So the goal is to just place the probe, and so have like a technician place the probe and then send the data off-site so they can be read. But the problem is the probes are very expensive, they're very heavy, and they're not heavy, but they're heavy in use. And so we still have to evolve in this. I'm just going to give you a few slides on what we do with this kind of setup, but not quite ULM. Well, we don't do ULM with this system. So with the same thinking, we created this company called ResolStroke, which has an ultrasound probe that is a matrix probe that looks 3D inside the brain. We don't look at the microcirculation, we look at the circulation and the perfusion. We use we inject bubbles, and this is for intensive care units. And now with this, it's possible, using similar process, to see the large vessels of the brain in 3D and within a few minutes in patients that were in the intensive care. And so, for example, this is a 3D reconstruction of the vessels that you can see across the skull. And another thing that's interesting about this is that you can pinpoint each of the position in the brain and have a perfusion curve. And this is very interesting for the doctors, because they can know if and by how much each of this part of the brain is perfused. So this is also the ongoing work. So you can have these structures through the brain. And what's interesting is that we've noticed that the patients that have low survival rate, because unfortunately in intensive care units a lot of patients are dying, had very peculiar patterns of perfusion before the death. So that's could be an element that we will push forward to do more analysis on the subject. So on this, I'm gonna finish. Thank you for your attention. I'm open for any more questions. Additional question with respect to this?
Yes. I definitely have questions while they think. The first question is, easy one, is basically on rats. Okay, they are much smaller than human. Are the microstructures basically the same as ours, but they have fewer of them, or are they just smaller?
It's slightly smaller. I think in human you would get capillaries down to maybe 5 micron, and rat could go down to 3 micron. Mm-hmm. But it cannot be much smaller because the size of the capillary is based on the red blood cell size. The red blood cell size is depending on the diffusion of oxygen, and this is a universal pattern in all. So basically, it's you have more microcirculation in human than in rats because of the diffusion of oxygen. So you need like a capillary for every 50 to 100 micron distance of tissue. So you have more.
Okay. And another question is, it's great that you are putting some data online, etc., so that people can try. Otherwise, it's people are never going to dip their toe into the field. But could you maybe describe to us what is actually available online? Because I assume that basically you have many processing steps.
Yeah.
And so I don't know if you just upload the raw data and the final step, or you have all the intermediate.
Well, that's why we use the term pipeline, because we give the whole pipeline except for the beamforming, which can be done by machine. The machine that you use for acquisition can also provide the beamforming. So passing from the hyperbole to the points, so that's done by the machine itself very often. So from that data, so we, for example, for the 2D imaging, we will provide 100,000 images that were done in one plane of the brain within 3 minutes. And then that's the beamformed image, so that's the ultrasound image. And then in the pipeline, you have the filtering to get the bubbles out. You have the localization process, you have the tracking process, and then you have the imaging process behind it. So it's a whole pipeline.
Okay. So presumably someone who is used to curves and temporal series could kind of jump in the middle of the pipeline and not have to do.
Yes. Well, the goal was so that people can change a part of the pipeline and also test if it's better with the metrics that are also provided. So there's also metrics that measure the resolution and things like that people can test if they change a piece of the pipeline, they can also test how they change it at the end.
Okay.
On the clinical integration side, how do you deal with the fact that you eventually going to need hundreds of terabytes of storage space and computing power?
Well, currently for example, in intensive care units, we had 10 terabytes of this space. So during the inclusion of the patients, we would empty the drives a few times and then process it afterward.
You flush.
Yes. Yeah. That's currently that's the issue. But we restricted like for a single acquisition now in human, we're about like 300 to 400 gigabytes. So it takes a while to fill like a 16 terabyte disk. Yeah, so we kind of reduce it to what we can use.
And you do need like several GPUs, or do you even need GPUs?
Oh yeah, it's a GPU, and it's it's work with 3090 level, so it's not. I mean, it's not. You don't need a 30,000 euros GPU. It still works like.
But that's still an issue to provide in a large scale unit.
Yeah, and it's part of the cost of the system. Yeah.
But it's cheaper than having to fill nitrogen in an MRI, just buy a PlayStation.
Yeah.
I mean, 130,000 GPUs, like one filling of helium for your MRI, right?
That's okay. So, I mean, a 3090, it's like €1,000, so you can definitely afford that.
But the goal is, in fact, I don't think we'll ever replace MRI. What will happen is that we will allow imaging in conditions that were not possible before. So basically, like the newborn, like they don't do MRIs every 6 hours. The intensive care units, they say we're going to image them like they spend like 2 weeks. We're going to image them 3 times, and that's it, because otherwise it's too risky for them, for the patients.
How do you measure the signal to noise ratio? I mean, in terms of so you are able now to have very thin capillaries.
Yeah.
Okay, what is the signal in this? Like, so your business is to do nice pictures. Okay, if you in the eye of statisticians, so okay, now we have terabytes of data. So definitely it's too high dimensional. So we have to lower the complexity of the data. Okay, what the hope to? So it was the question I asked to people like make light sheet imagery. It's okay, reminds me a lot of this. And now the question is, okay, are the image not too big to be like treated?
Well, if the question is what is the metric, I'm just trying to go back to something like I can do a simple analysis. Well, this, for example. If you just look at the grayscale behind it, you see that there's a point moving, like a PS, what we call a point square function for a system. Like the bubble is much smaller than this. So basically, the question of the SNR, you can measure it as, well, how strong is it with respect to baseline fluctuation of your signal? So that's how we measure that.
I mean SNR in terms of like more statistics. No, in statistics. So you are able to have a whole brain, a whole mouse brain with every capillary. Okay, nice. But what it's let's say a terabyte of data.
Yeah.
If you apply any linear complexity statistical methodology, it's already long.
Yeah.
So quadratic complexity, just forget about it. So if you want to treat your data, if you want to take information on your data, much more than just nice image, I can look around, I can zoom in, zoom out.
Yeah.
So what is it's maybe too large. So my point is, okay, you are acquiring data faster that we are able to trade it. Like, I mean, statistically.
Yes.
And that's the point on where is
well, that's why one of the limits currently is to try to get these biomarkers from. We have very simple process that gives you, like, for example, the distance to the nearest vessel. Okay, so that's how far you can get to a vessel that can perfuse this part. And we know that diffusion oxygen doesn't diffuse more than 50 to 100 microns. So we say that zone is hypoxic. So we basically use these basic algorithm, like saying that, well, if there's less ball in this area, it's less perfused, or if they go at different speed, or we can use the tortuosity of each of the tracks.
But is it used to drive the amount of data you are acquiring? I mean, maybe you need 10 seconds to acquire this information.
Yes.
But here, so the fact is that here I was asking, okay, you have to flush a 10 terabytes SSD drive to do this. So it's like or buy GPUs and say, well, okay, maybe it's too it's like overkill. Yeah, it's just overkill.
I mean, the strategy that we have right now is overkill, and to see what we can get from it, and then sparse it afterward, because we know it's overkill. But it's still doable. I mean, the system that we've conceived for the intensive care unit is by currently €100,000 in fabrication. It's not, well, no, actually much less than that for fabrication.
No, but maybe so you could advertise this as say, okay, if I want to send this in in a country where there is no huge facility, and there's like something which can be used anywhere. Okay.
Well, we're not at that stage yet, so we need to show that it works.
Yeah, I know. You have to advertise.
Yes.
Okay,
and then we have to say, okay, does it work? And now, how much can I reduce the amount of data to make it still work to the actual intended purpose? Because the intended purpose is not well known yet. The indication, I cannot say right now, this is the indication for this is that disease. So we're still in the building up phase. But obviously, at one point, currently you have ultrasound systems that are not doing this, but they're completely portable. They're connected to a phone. You get a phone in your hand. You have a probe that's connected by Bluetooth. You move around, and then on the cell phone you have a basic ultrasound image. So yeah, in many cases that's great. So that's basically a split where between right now you have like these point of care ultrasound, and you have IR hand ultrasound system like this that gives you like more possibility, and then eventually it will trickle. Well, that's a goal, right? It's a goal. You design something high end, and it will trickles like point of care ultrasound that you do now with a phone was something that was top end 40 years ago. So that's the principle, like this, that's the philosophy basically.
I also have a question on the technical side. What are people working on now? What's the bottleneck in terms of compute algorithm or whatever?
Well,
what's to upgrade?
I would say basically, well, the beamforming with GPUs it got pretty mature, but there are other types of beamforming with advanced algorithms that are just way too difficult. Then there's the tracking, there's the localization of the bubbles, how you separate it from tissue. And so this is based on, for example, singular value decomposition to try to separate how the bubble move and with respect to tissue. But
it's kind of off-the-shelf method so far, like the tracking.
They are, I mean, people are using other types, they're using common filters and things like that, but they, or AI to try to train what's supposed to, a bubble is supposed to look like. But it's not very well advanced. Like currently in my lab, I have a guy that's working on CNN so that we can see bubbles better in the tissue of the brain, in low SNR, low signal to noise ratio. And then you have other question of how, okay, so the bubbles move around. So that track is how do you make sure that it's a correct track, that it's not like jumping to the next bubble and things like that. So we use Hungarian method, but they're not necessarily great. And then the real target, in my view, is getting the biomarkers, because currently, like, we have very basic things like, okay, is the bubble there? How fast is the bubble going? How tortuous is the bubble? But everything more complex, we don't do. We don't use the fact that bubbles are passing through the same vessel, and they would have like a correlation in space, and that's not done.
So you say you need to go past the single, like bubble by bubble tracking, and more than like a moving field.
Yes.
So, okay. Yeah.
Exactly. Like see it as a network, and so that's and yeah, like the main target is mostly biomarkers. How to.
And do you use synthetic data? Because this is basically just PFS moving around. So could you use like just synthetic data to assess your algorithm?
Yes, you can actually you can actually, since it's a very tiny bubble, so it's a bit like a point-like structure, you can basically know what's the response of your system to that point-like system. So a lot of people are doing this simulation. Another way is just to take bubbles into open water and then just like acquire them. And so it's much faster than simulation.
Yeah, thank you.
So for example, for AI, what we do is we train the bubbles by adding bubbles that we've seen in free space onto a background tissue. That's how we train the model.
Okay, so probably we're good. Thanks a lot again, Olivier. It was fantastic.
Plaisir.